So up to now, what we have seen is that we have seen a simple five-stage pipeline, right? But in practice, pipelines are much more complex than what you have seen so far, right? It will have multiple stages of instruction fetch, and the execute stage is not necessarily just a single stage. It's in fact different functional units, each some are single stage, some are multiple stages, some are even non-pipelined, and so on. And similarly, the memory stage is also divided into multiple stages like the data fetch phase one, second phase, and then also tag check and so on. Right. So this is how a more realistic pipeline would look like. In fact, this is the pipeline structure of the MIPS R4000 processor. Right. And in this kind of pipelines, there are possibly structural hazards that can happen because different instructions which were started in different time step can actually go into the mem stage at the same time step, and that can cause some kind of a structural hazard. And one of these later instructions have to be stalled for a few cycles and so on. And in this particular pipeline, the branch target resolution and branch address calculation happens during the integer phase, which is actually 4 cycles into the deeper pipeline. Therefore, the branch stalls, right? Essentially, it incurs 3 branch stall cycles, right? And similarly, the load happens much later in the pipeline stage. And therefore, if the ith instruction and the I plus 1th instruction, if the ith instruction is a load and the I plus 1th instruction is dependent on that, then it has to be stalled by 3 cycles. Okay. And because different instructions take different amount of time during the execute stage, some instructions which were started at a later cycle can possibly go through and complete its execution even before some of the earlier instructions have completed their execution. And in this all case, also there could be war and war hazards that could happen because certain instructions can complete earlier and therefore can write into the write back stage even before the earlier instructions have read the values. Okay, now let's look at an important aspect of out of order issue, and let's talk about why it is important. Let's assume a sequence of instructions like this one over here, where you have a divide instruction which writes a result value in the F4 register, and that's actually a source operand for the subtract instruction, right? And therefore, the subtract instruction cannot go for execution until the F4, until the divide instruction, right, computes the result. And the divide is typically a very long pipeline. It could be like 32 cycles, right? And therefore, by the time the subtract can go into execution, it would be 30 plus cycles, right? Whereas the multiply instruction, which is following the subtract instruction, is not dependent either on the subtract instruction or on the divide instruction. The question is, can we allow the multiply instruction to go ahead and execute? This is what is called as out of order issue. Even though the subtract instruction, which is ahead in the program order, is stalled because it is dependent on the divide instruction, which has not completed its execution, right? Can we allow the multiply instruction to go ahead and execute? If you issue the multiply instruction out of program order even before the subtract is issued for execution, then that is essentially what is called as the out of order issue, right? If we can do that, then of course multiply can go ahead and execute and it can produce the result value, and then other instructions which are dependent on multiply can also go ahead and execute, right? So in order to achieve this, we need to do some kind of a reordering of instructions at runtime and try to issue these instructions out of program order. This is what is called as the dynamic instruction scheduling, right? And this is typically done by the underlying hardware or the runtime. Okay. And again, we are talking about issuing instructions out of order. Let's talk about, this, and then let's see what kind of complications it creates, whether you want to complete the instruction execution in program order or out of order and so on, out of order completion versus in order completion and so on. First thing is that to achieve this dynamic instruction scheduling, the instruction decode stage is divided into 2 stages. one called the decode stage, where the decode of the instruction takes place, and the other called the dispatch. After the instruction has been decoded, it is dispatched to what is called a reservation station or an issue queue, right? And up to dispatch, everything is in program order. That means that ith instruction is executed, ith instructions decode is executed, and then only I plus 1th instructions decode is executed. Similarly, ith instructions dispatch is executed, and then only I plus 1th instructions dispatch is executed, right? So both decode and dispatch happens in program order. And in dispatch, what happens is that after the instruction is decoded, it is moved into an appropriate reservation station, where it goes and waits for the functional unit to become available. And before that, it also waits for all the source operands to become available. So first thing is that it waits for all the source operands to become available. And when all the source operands for that instructions are available, then it can go from that to the execute stage, that is the functional unit, and then get executed. So the dispatch is essentially moving the instruction from the decode to the reservation station. Then when it waits at the reservation station, after it has received all its source operands, right? The hardware detects that all the source operands have been, for this particular instructions are now available. And if the corresponding functional unit is available, then it will issue this instruction right from the reservation station to the functional unit. So that is called the issue, right? So this is where we said that the instruction issue can happen out of program order, right? For example, the subtract may be waiting for its operands to be available, and it may be waiting in the reservation station, whereas the subsequent multiply instruction, all of whose operands are already available, would become ready, and the issue unit will then actually issue the multiply instruction right out of the program order, and multiply can go for execution. And when multiply completes its execution, it can either be allowed to write the result value in the destination register, or it's what it called, it can modify the architectural state of the machine even before subtract has completed its execution, or subtract has modified the architectural state of the machine. That is called out of order completion. Typically, we don't do out of order completion. We only do out of order execution, right? The result value of multiply is available for subsequent instructions to come to consume that, but it may not necessarily modify the destination register for various reasons, which we will explain later. Okay. Now, let's explain how the whole thing happens, right? So once the instructions are fetched, they are put into the instruction buffer, from where the decode and dispatch will happen, right? So the dispatch will take these instructions, and then based on the decode that it has done, it will put into one of those reservation stations. And these reservation stations are also divided in terms of the different functional units. For example, this could be the integer, right, reservation station. This could be the floating point reservation stations, and this could be the reservation stations for load store instructions. So when the decode unit decodes a load store instruction, it will dispatch into the load store reservation station. When it decodes, let's say, a floating point operation, it will dispatch into the floating point reservation station. Right, again, there are some fixed number of reservation stations which are available for each one of the functional units. So as long as there are enough space in the reservation stations, the instructions are dispatched into the respective reservation stations. When one of these reservation stations is full, and the next instruction to be dispatched, right, has to go to that particular reservation station, then of course it has to be stalled, right? But up to then, right, it can actually go ahead and dispatch those instructions, and then among the dispatched instructions, ready instructions can be issued to the respective functional unit even out of program order. For example, let us say the subtract and divide instructions, the subtract and multiply instruction that we talked about in the previous examples were dispatched one by one in program order to, let us say, these two reservation stations. And let's say the subtract instruction is waiting for the operand to become available because it's waiting for the divide operation to complete. to give its operand, one of its operand, therefore it will still be waiting. Whereas the multiply instruction, which is pushed into this reservation station over here, may have both of its operands available because both of its registers, right, were already written by some previous instructions which have already completed their execution. Therefore, those register values can be read and put into the reservation station, and those can be marked as ready. That is, when you are dispatching the instruction, you check the register file. If the registers are available, right, which is typically indicated by means of some kind of a bit, right, BC or available bit. If the available bit is set, then those register values are read and those values are stored in the reservation station. Now, when all the operands are available, that instruction becomes ready. And whenever the functional unit becomes available, then that instruction can be issued to that functional unit. So if the multiply instruction is issued to the functional unit when the subtract is waiting in the reservation station, this is out of order issue. Then the multiply instruction can go ahead and complete its execution after some number of cycles. And when it completes its execution, right, it will actually take the result value and it will send the result value both to the destination register as well as to all the other functional units and reservation stations, because some of these reservation stations may be waiting for the operands from the multiply, right, to be bypassed to them or to be forwarded to them. Correct? Therefore, there could have been, let's say, some other add instruction which may be waiting for the multiply to give its value. So that is being captured by means of this broadcast. And when that value is being broadcast, that respective reservation station which is waiting for the multiply to produce the result will actually capture that value and then set that bit to be ready. Right? This is how the dynamic instruction issue happens. Also, the same value would be broadcast to the registers and then could be written into the register file. There is a small complication here which I will explain in the next slide, right? But for the time being, you can assume that it is going to be written into the destination register, right? But then if I allow it to happen to write into the destination register, then this means that I am allowing the multiply to modify the architectural register even before subtract has completed its execution. So this is out of order completion. That's not really a good idea. We'll see why that is, and then we will see how to take care of that. But without, not worrying about it, this is how the instruction execution happens in out of order. Any questions here? I've very quickly gone through this detail, but okay. So I already explained all of these things. Let me just talk about why do we not allow out of order completion? Why do we want to have in order completion? This is because instruction execution could happen in a speculative manner. For example, consider the following sequence of instruction. There is a branch instruction, and let's say there is an add instruction, and then subsequently there is a subtract instruction. If the branch is predicted as not taken, and let's say the add instruction was executed, right? And let's say the branch instruction has not yet resolved. Do you allow these add instructions to go ahead and write the value in R3 register? Supposing, let's say you do allow that, then subsequently, if you figure out that this branch was predicted wrongly, and you should have not gone to the next instruction, but should have jumped to the subtract instruction, right? Then it means that you have modified the R3 register, right? Which is a speculative instruction, and you should not have, because the value of R3 has been lost, which was actually required for this subtract instruction, which is what is the correct instruction to be executed, right? So therefore, speculatively executed instructions should not be allowed to modify the architectural states of the register, correct? And this is one particular reason why you don't want to do out of order completion, right? Another reason might be that certain instructions might be raising exceptions. And when exceptions are raised, then the instruction which is raising the exception, the first thing is that the exceptions are handled, and then the instructions which are raising the exceptions will be re-executed, and all subsequent instructions have to be executed one after the other. So for example, let us say that this add instruction was executed, has completed its execution. If you allow it to modify the R5 value, and subsequently if the divide instruction raises an exception, then after handling the exception, you have to re-execute the divide instruction, and then you have to re-execute the add instruction and every other instruction. That would again cause complications because the R5 value was already modified. So because of these reasons, what you tend to do is that you allow the instructions to execute out of order, produce the results, and even forward the results to other instructions which are waiting for that. But do not modify the architectural state. Do not modify register 5. Register 5 would still contain the old value even though this instruction has completed its execution, right? And register 5 will actually have the new value only after this instruction has completed its execution and has modified R1. And after that, the next instruction will complete. So this is what is called as in-order completion of writing the result value. So we also call this as committing or completion, in-order completion, right? Which is essentially modifying the architectural state of the machine. Okay, so how is this achieved? Before I go to how is this achieved, let me also talk about exception handling, which is another aspect. The third aspect that we want to also address in order issue and execution is that if there are different instructions which can raise exceptions, then even though you may be executing instructions in a pipelined manner and in an out of order execution manner, you still want the processor to see these exceptions in the same order as they would happen in a sequential execution. For example, if there is a multi instruction and a divide instruction, right? Supposing, let's say, the divide instruction causes an exception first, and then later on, let's say the multi instruction which was waiting on something is causing an exception. You don't want the exceptions to be seen in the order of divide followed by multiply. If the program order is multiply followed by divide, then the exception should also be seen in the same order. This is what is called as precise exception handling. And this is also required for various reasons. Let me not go into those details now, right? So processors would also try to implement precise exceptions, and even for this purpose, right, you want to have in-order completion. Okay. So with those things, let me now quickly talk about how this in-order completion is achieved, right? Remember, I talked about these reservation stations and then functional units, and when the functional units complete their execution, they broadcast the results to all the reservation stations, as well as they write the result value into the register file. But if I allow it to write into the register file, and if instructions complete out of order, then I'm also doing out of order completion, which is not what is desired. So instead, what I would do is that I would allow these values to be written into some kind of a buffer, right? And this is basically a first in, first out buffer. And from this first in, first out buffer, I will take the values and then write it into the appropriate registers in program order. And when I do that, I am modifying the architectural states in program order, right? So essentially, the reorder buffer is an in-between location where the result values are written, and the result values can be read from that in-between location, right, for other future instructions, and can be used for their computations. But only thing is that that result value is not written into the R5 register. It will be written into the R5 register when that instruction, for example, when that add instruction becomes the head of the reorder buffer. Right? When it becomes the head of the reorder buffer, all other previous instructions, all other instructions which are ahead of this instruction in the program order have already completed and gone out of the reorder buffer. So this is the next instruction to complete in program order. Therefore, then it will go and write the value into the R5 register. So in a sense, what you are doing is that you are producing the values out of order, saving it in this reorder buffer, Okay, and then you are also using it for all other future instructions from this reorder buffer. But only thing is that when you are modifying the architectural registers, when you are modifying the R5 register, you are doing it in program order. Therefore, if at any point in time you figured out that the add instruction was speculatively executed and should not modify or should not have been executed in the first place, if you discard the reorder buffer location, right, the R5 register would indeed contain the old value, and you could go ahead and execute the target location and the correct from the correct path or instructions from the correct path, and you could still preserve the semantics of your program. Correct? So if you have not modified the R5 register and the previous instruction divide was causing an exception, you could actually handle the exception, execute the divide instruction, and after that again go and re-execute the add instructions and so on and so forth. Because the R5 value was not modified, you are still good to go, right? So that's essentially what is done by this reorder buffer over here. This is a very important structure in out of order issue, and this is what is used to also implement register renaming in some way. Because when the R5's value is produced, right, it is not written into the R5 register, but is written into the reorder buffer location. Supposing, let's say that there is a subsequent instruction which is using R5 as the source operand, then it will actually try to read the value from the reorder buffer location rather than from the register file, because the register will indicate that it is still busy. That means that the value has not been written into the R5 location, but then it will say that R5 corresponds to reorder buffer location some k, and therefore it will actually go and read it from that location. This is what is called the dynamic register renaming. This is one particular way of implementing dynamic register renaming using the reorder buffer. Professor Madhu Mutyam will talk about superscalar processors, where he will also talk about again register renaming and register renaming using physical registers and so on. Okay, so that kind of completes our discussions on out of order issue. I've already taken about 20-25 minutes more than what I expected to do. But still, if you have any quick questions on this, I will answer that before I go to the next part, which is on caches.
Sir, I have a question.
Yeah.
So you mentioned a speculative execution bunch of times in these
Right.
two things, right?
Right.
So, but those are two different things, right?
What two things?
Out of order execution and speculative execution.
Oh, okay. Yeah. Out of order execution is essentially issuing instructions out of program order, right? Speculative
Yes.
execution happens because you have a branch instruction and you predicted the branch. In this particular case, we are talking about the branch predicted as not taken, and then I'm trying to execute the next instruction. So this is a speculative instruction. Okay, this is a speculative instruction. Okay, whereas in this case, there is a divide instruction and there is an add instruction. Maybe the divide instruction was waiting for one of the operands to become available, and the add instruction, right, had all its operands available and it can go for execution. This is not a speculatively executed instruction. This is an instruction which is executed out of order.
Yes.
Correct? It's a non-speculative instruction, but still you don't allow this R5 to be modified because of various other reasons. Right? In general, you implement in-order completion, whether it is speculatively executed instructions or instructions which are executed out of order. Okay?
Okay.
Yeah.
Yeah. I mean, Spectre vulnerability happened due to this speculative execution.
You're talking about the Spectre and Meltdown?
Yes. Yes. So I mean, in that case, also completion didn't happen. That I mean, the architectural state was accessed due to side channel.
It's not about the completion part. I think there it is more about speculatively executed instructions causing something else in the caches. Okay, that requires a little bit more detailed discussion. Maybe we should take it offline.
Okay, thank you.
Right? Yeah. Any other questions?
If you could just clarify about what exactly the reorder buffer contains, what kind of information it holds.
Okay. So you can just think of the reorder buffer as Okay, so simplest thing is to say which register, means what is the destination register in which the value has to go to, and what is the instruction which has produced this value, and what is the value. So maybe these three things, right? So if the ith instruction has produced a result value for R5 register and the value is 23, then I, R5 and 23 are the three things that are stored in the reorder buffer. Correct? I specifies the program order, R5 specifies the destination register, and 23 specifies the value.
Right. But there also has to be this notion of ordering inside the buffer itself, right?
First in, first out.
Yeah, but then but the example that you said, a previous instruction giving an exception at a later point.
Correct. So for example, let's say that if this is the again, I'm talking about the dynamic instruction order. Correct.
Mm-hmm.
So let's say that let's say the buffer is like filled in this way. So this is the ith instruction. Okay.
Right.
This will be the I plus 1th instruction. So when the instructions are dispatched, these locations are reserved. Right. When the ith instruction is dispatched, that particular location is reserved. When the I plus 1th instruction is dispatched, this location is reserved for that. When the I plus 2nd instruction is dispatched, this location is reserved for that, and so on.
Right.
Correct?
Got it.
Huh? So at that point in time, I will simply say the destination register is R5. I don't know the value. I know it is I plus first instruction. I know it is R5 register, but I don't know the value. Correct? Huh? Any instruction which is dependent on this R5, right, would say that it has to read the value from reorder buffer location, this one, as and when the value becomes available, not before that. Okay. So again, there are additional informations which are being maintained. Okay.
Right. Got it.
Yeah. Any other questions?
Yes, I have one more question.
Sure.
So, I mean, apart from the complexity that it adds, this outer order execution that it adds on the hardware end, let's say hardware design have to do all this design. Do you think any other reason why, let's say, low-end processor like ARM Cortex M does not implement out of order?
It's the complexity. It's the complexity, and yeah, it's a complexity and the associated power consumption compared to the benefits that you get out of that, right? But again, think of, many of these ARM processors that you talk about may not have complete out of order issue and execution, but they still have in order issue, right? In order issue is at least half as complex as out of order issue, if I have to say. But it's not like it's a simple pipeline. It's much more than that. Okay. It's yeah. There are many details which I couldn't go into the in great levels. But again, when I think Professor Madhu Mutyam talks about superscalar processors, he will talk about out of order, in order issue, out of order issue, where the queues are maintained and what's happening there, and so on and so forth. Right? But still, you have to really figure out all the dependencies at runtime, and you have to make sure when the instruction becomes ready. Even in an in-order issue processor, right? Just because you are issuing in order, it doesn't mean that you will somehow be able to figure out the dependencies easily. The dependency, right, part of it is at least as complex as the out of order issue part. Okay. So the right way to think about is that in order issues, you assume it to be 50% complex, out of order issues 100% complex. It's not like in order issue is like 5% complex and out of order issues 100% complex. No, that's not the way to look at it. All right.
Sure. Thank you.
Yeah. Okay. So let's stop this discussion over here. and then switch to the next set of slides, because at least I want to cover a reasonable part. Again, I'm going to stop sharing and then start sharing the new set of slides. So bear with me for a minute. Sorry, I should have done this in the first place. This is, give me a second. Okay, are you able to see the new set of slides now on memory hierarchy?
Yes.
Okay, so let's see what's the agenda here. We'll again give a very quick introduction to memory and then get on to cache organizations, most of which you would have seen in your undergraduate program. So I'm going to only do a quick review of that. Then we'll also talk about how to improve cache performance. Then let's talk about virtual memory. Again, this is a quick overview of what you have seen in your undergraduate program, and then some new complexities or some new things, information added to that. And then we'll talk about how virtual memory complicate, about caches and what are the different types of caches that we can talk about. Again, we will see to what extent we can see all of them in the next 1 hour or so. You all know about this memory hierarchy. I don't want to go into the details. You have the processor registers, which are fewer in number. Then you have caches, which again, now in today's context, you have multiple levels like L1, L2, L3, and the size of which varies from a few kilobytes to maybe about a few hundred kilobytes to maybe even about to few tens of megabytes when you talk about an L3 cache or something like that. Then we have main memory, which is in the order of, in today's context, which is in the order of a few gigabyte to few tens of gigabytes, so to say. Then, of course, you have the secondary storage and so on. As you go down the memory hierarchy, the size increases, but the access time also increases. Okay. And as you go up the hierarchy, the size decreases and the access time is faster. Okay. Again, the same information. If you talk about processor registers, they are fewer in number and they can be accessed in less than a cycle time, sub-cycle access time. Then you talk about your L1, L2, L3 caches, and today all of these levels are on chip, and their sizes vary from few tens of kilobytes to maybe about few megabytes. And the access time varies from a couple of cycles to maybe about few tens of cycles, maybe 10 cycles or 20 cycles and so on. Whereas as opposed to this, when you talk about main memory is in the order of a few hundreds of megabytes to maybe even gigabytes. And its access time is actually not tens of cycles. This is wrong. 1 0 is missing. It's in the order of hundreds of cycles, hundreds of process cycles. Okay. And of course, you have secondary storage, which is disk, which is accessed in actually several millions of cycles, because it will be in the order of tens of milliseconds. So we're not going to worry about secondary storage, but we'll talk a little bit about memory. Why are we talking about memory hierarchy and why is it important? We already saw about Moore's law, or sorry, we didn't see, but you all would know about Moore's law, which essentially talks about the number of transistors increasing in a chip, and therefore, there is a corresponding improvement in processor performance, which is doubling every 18 months. So the top curve really shows the processor performance improving, whereas the bottom curve shows how the memory performance has improved over the years. Memory performance improves roughly by about 10 to 15% every year, and therefore, if you look at it compared to the processor performance, memory performance is only slowly increasing. What is really causing concern is this widening gap between the processor performance and memory performance. And this widening gap between these two entities, the processor and the memory and their performance, has to be accounted for or has to be addressed using the memory hierarchy. Okay, that is where the caches come into picture. And as you all know, caches exploit the principle of locality. right? And the locality essentially says that 90% of, and locality essentially follows from the 90-10 rule, which says that the 90% of the execution time is spent in 10% of the code. And when we talk about locality in caches, we talk about temporal locality, which essentially means the location which was accessed in the past is again accessed in the future. Whereas spatial locality refers to the fact that the location which was accessed in the past, nearby locations to that would be accessed in the future, right? And in caches, we try to exploit this temporal and spatial locality by keeping the recently accessed locations as well as keeping the nearby locations in a faster storage, which is what is called as the cache, right? And we also know that both temporal and spatial locality, right, are exhibited both in instruction access as well as in data access. Okay, now let's talk about different kinds of cache organization. You know that there is caches could be organized either as a direct mapped cache or as a set associative cache or as an associative cache. And depending on how the cache is organized, you also try to find out where the data is located, or how to find out where the data would be located in the cache, right? And of course, when a new block has to be placed in the cache, which block has to be replaced? What is the replacement policy? And lastly, one also talks about what happens when you want to do a write to a memory location. If the location is a hit in the cache, then what do you do? If the location is missing a cache, then what do you do? Right? In the case of a hit, you say that whether the write has to be done only in the cache or it also has to be done in the memory. Right? So when do you do the write back? That's the policy that you talk about. Right? In the case of a cache miss, do you bring the data from the memory to the cache and then do the write, or do you directly write into the memory location? That essentially is whether you do a write allocate or a write no allocate. Okay. Let's also quickly review some of the terminologies that we use in caches. For example, you talk about a cache hit if the data is found in the cache. And if the data is not found in the cache, then it is a cache miss. Then correspondingly, we talk about a hit ratio or a miss ratio. Hit ratio is basically the ratio of number of hits to the number of memory accesses. And miss ratio is 1 minus hit ratio. Hit time refers to the time it takes to access the data if it is found in the cache, right? To access the data from the cache, whatever is the time it takes, is the hit time. Typically, if the data is available in your L1 cache, then your hit time is 1 or 2 cycles, right? Miss penalty refers to the time it takes to bring the data from the next level in your storage. If it is next level is memory, then it's the time taken to bring the data from the memory to the L1 cache, right? And when you are bringing the data from the memory to L1 cache, you are not just bringing the required data, but you are bringing the required cache block, right? So what is the time it takes to bring that cache block or bring that memory block into the cache? What is the time it takes? That's the miss penalty. And you talk about this average memory access time. We will again come back to this average memory access time little later on, after we have discussed some examples of the cache organization and so on. In the interest of time, what I thought is that since we are only doing a review, instead of reviewing all three organizations, I will actually review the set associative organization. And then from there, one can easily see what one would do for a direct mapped cache or what one would do for a fully associative cache. In the case of a set associative cache, the cache blocks, right, are divided into a number of sets, each set having k number of blocks if the cache is a k-way associative cache. For example, in a two-way associative cache, each set would contain 2 blocks. In this particular example, if the cache contains a total of, let's say, 8 blocks, and if you want to organize it as a two-way set associative cache, then each set would contain 2 blocks, and then there will be 4 sets. Now, in a set associative organization, each memory block is mapped exactly to one particular set. and within that set it can be in any one of those blocks. So for example here, right, memory block 3, memory block 7, memory block 11 and memory block 15, they are all mapped to cache set 3. Similarly, memory block 0, 4, 8 and 12 would be mapped to cache block 0. And okay, sorry. So this mapping, as you can see, is typically achieved using a mod operation. Take the memory block number, divide by the number of sets, you know which set it gets mapped to. Right, whatever is your reminder, that tells you to which set it will get mapped to. Okay. So a direct mapped cache is one in which in each set you have exactly one block. Right. So so if you have 8 memory blocks, then you will have 8 sets. If it is a fully associative cache, then it has only one set and all the blocks are in that set. So every block can map to that one particular set. Right. So that's the easiest way of understanding the other organizations. So in the case of a set associative cache, how do you figure out whether a particular memory block is in the cache or not? Right? Then you take the memory block's address and then you divide them into these individual fields called the offset field, the set index field, and then the tag field. So let's see how we can do that, and let's see that with the help of a example. Right? Let's assume 32 bits of address, and let's assume that we have a 16 kilobyte cache. And each cache block or memory block is 32 bytes, which means that, right, 32 consecutive bytes form the memory block. And let's assume it is a two-way set associative cache. So the first thing that you find out is that how many sets are there in the cache. So if you take the cache size divided by the cache line size and divided by the number of associativity, then you essentially get, right, the number of cache blocks divided by 2. The number of cache blocks is 16k divided by 32. That divided by 2 is essentially 256. Okay. And then to identify the specific byte within the memory block, since there are 32 bytes in the block, you need 5 bits for that. Okay. So the offset is essentially 5 bits. And to index one of the sets, right, there are 256 sets, so you need 8 bits for them. The remaining bits are what are called the tag bits. Okay, so if I take a 32-bit address, 5 bits for the offset because there are 32 bytes, 2 to the power 5 is 32, and there are 256 sets. There are 512 blocks, but there are only 256 sets because it's a two-way set associative cache. So therefore, the index bits, right, are 8. The remaining bits are the tag bits. So you take a 32-bit address and then you divide it like this. Then this is the way by which you will see whether the particular memory block is in the cache or not. Right? You use the index bits. You index into the cache. Because it's a two-way set associative cache, in that particular set there are going to be 2 blocks. Then in each one of those blocks you check whether the tag that is saved in there matches with the tag of the address that you want to access. If those 19 bits are identical and the valid bit is set, that means that this particular block essentially stores the memory block that you are looking for. Only one of the blocks in that set will actually have that tag matching. The other one will not have the tag matching. So either one of this would match, and whichever one which is matching is the one which is going to give you the data. So if at least, not at least, if one of them matches, then you say it is a cache hit, and then from that particular cache block, right, and with that given offset you index and then take that particular word out and then you give that as the data. Okay. If neither of these tags match or if the valid bits are not true, then it is a case of a cache miss, in which case the data is not available in the cache at that level. Then you either have to go to the next higher level or to the next. This is exactly how you do accessing in a set associative cache. If it's a direct map to cache, then there is only one block, right? There is only one block per set. In a fully associative cache, there will be as many blocks as the size of the cache. And a fully associative cache is actually a very hard thing to implement from a hardware perspective. So we don't talk about that. Okay. Now the next question is that when you are looking for a block, the block is not there in the cache, and you have to bring the block from the next higher level and put it into the cache or put it into that particular set. And the question is, in that set, which block will you use for writing, or which block will you replace with the new map, with the new data? If it is a direct map to cache, then the choice is obvious because there is only one block and you have to write it in that location. If it's a two-way set associative cache or a four-way set associative cache, then one of those four locations has to be chosen. And the way in which you can choose them is based on either first in, first out order, or the least recently used order, whichever data which has not been used in that set for a long time, you will replace that particular data. Or it could even be a random policy. It could be like one of those four locations chosen randomly. Typically, it is the least recently used policy which was used, right, for doing the replacement, particularly for the L1 cache, right? And to implement the least recently used policy, there are some additional bits which are used for implementing this. Let's not go into those details now. Okay, let's also quickly talk about what happens on a write, right? If the data is already available in the cache block and this is a location that you want to write, then you can either write that value in the cache as well as in the memory or in the next levels of hierarchy, which is what is called as write through. And when you do a write through, you're essentially making sure that both the cache and the memory locations, like they have consistent values and the most recent or most up-to-date values, right? There are no stale values in the cache. But the problem with this approach is that write to memory is slower. And then if a particular location is being repeatedly written, then every one of these write actually percolates all the way to memory, which is inefficient. Instead, you could actually write to the cache multiple times, and yet when you are replacing this block from the cache, you can write it to the memory once, right? So that would have been much more efficient than the write through policy. So the other policy, which is what is called the write back policy, in which case you only write the value in the cache and not the memory. The memory becomes stale and only the cache has the up-to-date value. This is where the dirty bit in the cache is useful, metadata dirty bit. This essentially says that this cache block has been modified. So at the time of a replacement, when this particular block is replaced, if it is a dirty block, then the value, right, which has been modified in the cache has to be reflected into the memory before you bring in the new block, right? So that's essentially what happens in the case of a write back policy. The advantage of the write back policy is that since you only write to the cache, the writes are faster and you don't necessarily do multiple writes into the memory. Okay, those are the advantages. Now, if you want to do a write and let's say the memory block is not there in the cache, then this is a write miss. Then in which case the policy could either be to allocate this block into the cache, that means that bring that block from the memory into the cache, then it becomes a write hit, then depending on whether it's a write back or write through, you do the write. Or it could be a write no allocate policy, in which case you decide not to bring the data into the cache and directly go and write into the memory. That is also possible, right? Both the write back and write through versus write allocate and write no allocate are actually orthogonal to each other, and you could have any combinations of these things. Typically, a write allocate with a write back is what is followed, or a write no allocate with write through is what is being followed. Okay, now in order for us to understand the performance of the caches, let's look at the different types of misses that could happen in a cache, right? Since the data is initially in the memory and has to be brought into the cache at the first time when it is being accessed, right? The first access is always going to be a miss, and this miss is what is called as the cold miss or the compulsory miss, right? And the cold miss or the compulsory miss happens, the data is going to be brought in, and as we know, the data is not just the word that you are accessing, it's the entire memory block, right? So nearby data is also being brought in. If the memory block is larger, then more data is going to be brought in, and therefore the capacity or sorry, and therefore the compulsory or cold miss is going to be reduced. So increasing the block size would actually reduce the compulsory misses. The second type of miss is what is called as the capacity miss, and these misses happen because of the limited capacity of the cache. Remember, the caches are of size few kilobytes, whereas the main memory is of size few megabytes or maybe even few gigabytes. So not all the entries that you are trying to access could be fitted into your cache. So some entries are going to come and replace some other entries because the capacity is limited. And later on, if these evicted entries are being accessed, they are going to incur a miss. That miss is going to be accounted as the capacity miss because they got evicted because there wasn't enough space in the cache, right? So those misses are called capacity misses. The third kind of misses is what are called conflict misses, and these happens because, right, cache blocks or memory blocks get mapped to a fixed set, right? Each block gets mapped to a fixed set. So if two different blocks are getting mapped to the same set, or let's say if multiple blocks are getting mapped to the same set, and you can only hold, let's say, if it is a four-way associative cache at a given time, you can only hold four of these blocks, then it is going to replace one of the existing blocks, right? And if that block is accessed again in future, you are going to have a miss for that. Such kinds of misses are called conflict misses. They happen because multiple blocks get mapped to the same set and only some limited number of them can be held together, right? So such misses are called conflict misses. So if you look at all the misses in your cache, then they could be classified into one of them. They are either cold misses because they are accessed for the first time and you are incurring the misses. If it is not the first time, then it could either be because they were evicted because of limited capacity, or they were evicted because of the fact that they conflicted with some other locations, right? Okay, now let's talk about different ways of improving the cache performance. But for that, first thing we will try to do is that we will try to understand what is cache performance. So when we talk about cache performance, essentially our idea is that caches are implemented to reduce the average memory access time, reduce the memory access time on an average, right? So when I have a cache, how do I talk about what is the average memory access time? If the data is always available in my cache, then my memory access time would reduce to that of a hit time, right? But if it's available, let's say 90% of the time, and only in the remaining 10% of the time it's not available in my cache, of course, always I first check in the cache, and only after I find out that it is not available in the cache, I go to the next level, right? Let's say the next level is memory. So initially, I just incur what is called a hit time, and if the data is available, I get the data. If the data is not available, then after the hit time, I get to know that it is a cache miss, right? Then in the remaining 10% of the cases, I incur what is called the miss penalty, which is the amount of time it takes to bring the data, right, from the memory block to the cache and then access the required data. Therefore, in this particular case, right, if 10% of the time I'm going to incur the miss penalty, and 100% of the time I'm also going to incur the hit time. That's essentially what is the average memory access time. So if you want to reduce the average memory access time, you have to reduce the hit time. You also have to reduce the miss rate and the miss penalty, or at least you have to reduce one or more of them without significantly increasing the others. So to improve the performance of the cache, you have to decrease the hit time, you have to decrease the miss ratio, you have to decrease the miss penalty, right? Any one of them or any combinations of them. But more importantly, when you are reducing one of them, you should not increase the other one significantly. If you happen to increase the other one significantly, then overall you may not necessarily gain any benefit. Okay, that's what you need to be careful about. Okay, so let's look at these three components, right? These three components, hit time, miss ratio, and miss penalty, and quickly see how you can improve them. To reduce hit time, right, you have to typically implement a smaller cache and you have to implement a direct mapped cache. In both of these cases, the hit time would really reduce. To reduce the miss rate, it's the other way around. You have to increase the cache size, you have to increase the associativity, you have to increase the cache block size, and so on. Okay, but increasing the cache block size would actually increase the miss penalty. This is what I said, that when you are trying to decrease one, you should not try to increase the other one significantly. Okay. One other technique that was used was what is called a victim cache, which is a small cache which is kept along with the main cache, and any block which was evicted was actually put into the victim cache and held there for some amount of time, right? And that often helps to reduce the miss penalty, right? Because they were always found in the victim cache and they can be brought back quickly. Okay. Another idea which was used very effectively to reduce the miss rate is to do prefetching, right? By knowing the past accesses, right, you try to predict what would be the future accesses or which memory locations are likely to be accessed in future, and you try to bring those data into your cache. Again, there are both positives and negatives in doing this. The positive is that, of course, you will bring in the data ahead of time, and therefore that by the time that you access the data would be in the cache and you would have a cache hit. But for this, your prediction has to be correct, and if your prediction is wrong, you will actually bring in unnecessary data into the cache, which might again throw away some useful data out of the cache. You will also increase your memory bandwidth and so on and so forth, right? So those are the other things about prefetching. Of course, one can do a lot of compiler transformations like loop interchange, loop tiling, etc., to improve the locality in your program and therefore to reduce the miss rate. Other techniques that you do to reduce the miss penalty is to decrease the size of the cache block. But if you decrease the size of the cache block, of course, you will increase the compulsory misses. Okay. Of course, there are these other techniques like increasing the cache block size, but implementing certain things called sub-blocking and other things. I will not go into the details because these are all some small techniques which are used for implementing them. Okay, one other important technique that we will talk about in detail is to implement multiple levels of caches, right? So this I will particularly talk about in one of the following slides and then go into some levels of details. And of course, you also talk about what are called non-blocking caches. So we'll actually talk about these two things, multiple cache levels and non-blocking caches, in the next few slides. Okay, my slides are appearing out of order. Okay, animation is appearing out of order. So what are these non-blocking caches? So when you are trying to access a memory location, you try to first access the cache. If the data is available from the cache, you can access it. But if the data is not available, then this request is going to be forwarded to the memory from which the data is going to be brought into the cache, and then again from the cache you will access the data. But when you are when you are experiencing a miss, would the processor be allowed to access other memory locations in the cache? If it is allowed to access other memory locations, then that particular cache is what is called as a non-blocking cache. That is, when it is servicing the request of a miss, it's actually receiving other requests and it is processing them, right? So it could process other hits when it is experiencing a miss, or it could process other misses, right? Hit under multiple misses also, other misses also over this miss. It is possible to do that. So here essentially what happens is that when a processor requests for certain memory location, if that location is not there in the cache, then the cache experiences what is called a cache miss, and this request is forwarded to the memory. And when it is forwarded to the memory, the information is tracked in one of these what are called miss status holding register or MSHR, which says that a request has been initiated to bring this particular memory block into the cache. That information is stored in the MSHR register. It also stores to which register the value has to go into and so on. Whenever there is a future access, if that future access is for a different memory block, right, then of course the cache is indexed, and if that block is available, you can service that request. If the block is not available, you will again create one more MSHR entry and then send that request also to the memory block. If let's say a third request which comes for one of the same blocks but for a different memory location, right? Maybe you have accessed the ith location in block K. Now you want to access the I plus second location in the same block, right? This is a different load instruction. Now, again, you are going to experience a cache miss because the kth block is not there in the cache. But then when you look at the MSHRs, you're going to figure out that the request has already been forwarded to the memory and the kth block is anyway being fetched. So in that case, this miss is called a secondary miss and is held along with the primary miss in the miss status holding register. So when the primary miss is serviced, the secondary miss is also serviced because the primary miss is going to bring the entire block, not just the data, but the entire block from which the secondary miss can also be satisfied. Such kinds of caches are what are called as the non-blocking caches. Okay. Now let's look at multi-level caches. As we mentioned earlier, to improve the performance of caches, you want to design small caches. You want to design caches with very low hit time. But small caches with very low hit time and let's say low associativity also means that they will have a large number of misses. The miss rates would be high, right? Therefore, to reduce the impact of this larger miss rate, what you want to do is that you want to reduce the miss penalty. So what you do is that you design an L1 cache which is smaller, which has a lower associativity. But to reduce the miss penalty of this cache, you actually design the next level of the cache hierarchy, right? Which is an L2 cache, which is larger, okay? But it can actually service the request faster than the memory. Okay, so this is typically the philosophy between multi-level caches. The lower level cache, L1 cache, okay, gives you a low hit time and also low hit time. The low hit time is really important because the low hit time is often linked to the process cycle time. Okay, therefore you want to have your L1 cache to be having a hit time which is closer to the process cycle time. Whereas the L2 cache is larger and it actually has fewer misses or lower miss rate, and it can actually satisfy L1's miss penalty much faster than compared to memory. Okay, so typically the L1 is direct mapped and a few kilobytes, whereas the L2 is larger and is set associative and so on. So if you look at the Intel Skylake processor, it's L1 cache, right? It has a separate instruction cache and a data cache, each of size 32 kilobytes. And it's actually fairly decently associative. Whereas the L2 cache is much larger, 256 kilobytes, and the L3 cache is about 2 megabytes per core. And they are also set associative. Okay. So if you want to put these things together, your organization is going to look like this. The processor issues a memory request, and that memory request is being looked at in the L1 cache. If it is available in the L1 cache or if it is a hit in the L1 cache, then it is immediately serviced. If it is a miss in the L1 cache, then it goes to the next level cache and then it is looked up there. If it hits in that thing, then the data is brought, for simplicity, let's say that is brought from the L2 cache into the L1 cache and then from there service to the CPU. Okay. If it is not there in the L2 cache, then of course you go and look into the memory, bring it from the memory to the L2 cache and then from the L2 cache to the L1 cache. And at different levels, the access times are very different. Okay. So there are certain things that we haven't yet seen. One is about the memory management unit. We'll come to it little later on. And the other thing is, whenever I want to access the data, do I always bring from the memory to the L2 cache and then from the L2 cache to the L1 cache, or do I directly from the memory to the L1 cache? That's something that we want to see. We will see those things little later. Okay. So maybe maybe just finish this slide and then take one or two questions before we move forward. Now let's once again revisit the average memory access time. If you have one level of cache, then the average memory access time is exactly like what we saw earlier, right? Hit time plus miss rate into miss penalty. But if let's say if you have two levels of access time, if you have two levels of caches, then what would happen to the average memory access time? Right? The average memory access time can still be looked at in the same way as you looked at for one level of cache. But only thing is that this miss penalty L1 is no longer going to be the miss penalty of getting the data from the memory, because this miss penalty could also be satisfied from the L2 cache. Therefore, the miss penalty of L1 is actually the hit time from L2. But then not all data would be found in L2 also. Therefore, some data which is not there in L2, which is basically determined by the miss rate of L2, right, there the data has to come from the memory. So that is the miss penalty. So you multiply the miss rate at L2 multiplied by the miss penalty experienced by L2, right, and that gives you the miss penalty for L1. So if you substitute this miss penalty over here, then you will get the average memory access time for the two level caches, which is basically hit time at L1 plus miss rate of L1 multiplied by hit time at L2 plus miss rate at L2 multiplied by miss penalty. I think this has to be multiplied. This is not plus. Okay, sorry, there's a mistake here. This has to be multiplied. Okay, so let me just stop here and then take questions before I go to other complications. Are there any quick questions here so far in the caches? We kind of rushed through this because most of it you are familiar with. I just wanted to quickly recall these things.
Sir, could you please go back to that reducing miss penalty slide? That you give an example of Skylake processor.
There are multiple slides. So reducing the miss penalties, then?
It continued. Yes, in the slide you give an example of Intel Skylake processor.
Oh, Intel Skylake processor, which was actually in this slide, I believe. Yeah.
Yes, yes. So in this case, in line first, you mentioned that first cache should be small and associativity should also be small.
Correct. Typically, that's why I said that typically L1 cache is direct mapped, right, and small or small associative. But in the case of Skylake, it's an aggressive design. They have put that L1 cache as 8-way associative. In fact, L2's associativity is relatively lower. Again, these are all done, doing a lot of experiments, seeing, what is the hardware complexity, what can be accomplished, and what gives performance, and so on and so forth.
Yeah, I believe they might be using simulators and other tools before making these decisions. Right?
Yeah.
Okay. And one more thing, you mentioned this thing as 64 byte line as private. So I'm assuming that this private is, let's say, per core private, or let's say a single cache block.
Yeah, it's not the line is private. It's the L1 cache is private, the L2 cache is private, and the L3 cache is shared.
Okay.
Right? It's not about the line, it's about the cache. Any other questions from anybody else? Okay. Let's see. Right. So when you talk about this multiple levels of caches, then you talk about what are called inclusive caches versus exclusive caches. Inclusive caches are one in which you say that if a block is found in, let us say, an L2 cache, a higher level cache, then it will also be found in the lower level cache, or it's actually the other way around. Let me just put it correctly, right? So every block which exists in the lower level also exists in all subsequent levels. So for example, if I find a block in L1 cache, then I should necessarily find this block also in L2 and L3 caches. Therefore, whenever a block is evicted from a higher level cache like an L2 or an L3 cache, we have to make sure that it is also evicted from the lower level caches. Such kinds of caches are called inclusive caches. That means that the L2 cache, right, um, whatever is in L2 cache, I mean, it's actually the other word. Whatever is in L1 cache is also there in L2 cache, and whatever is in L2 cache is also there in L3 cache. That is why the inclusion comes into picture, right? There are certain advantages of inclusive caches. It's easy when you want to implement cache coherence protocols, but there are certain disadvantages also, because to maintain inclusiveness, you have to invalidate certain lines from the cache, and inclusiveness also means that you are not utilizing all the cache space effectively, right? So think of inclusion as in this way, like every level, right, is actually a subset of the next higher level. So L1 is a subset of L2, L2 is a subset of L3, and so on, right? Therefore, your effective capacity is only L2, L3, right? Whereas in the case of an exclusive cache, you necessarily ensure that whatever is in L2, right? I mean, whatever is there in any level, it is not there in any of the other levels. Okay, the block contains so the blocks contained in each levels are mutually exclusive. Okay, so in this particular case, when a particular block is not available in the L1 cache, you look it up for in the L2 cache. If it is there in the L2 cache, then you move it from the L2 cache to the L1 cache, and then remove it from the L2 cache, or that entry is replaced from the L2 cache. Similarly, if it is there in L3 but not in L2 or L1, then you move it directly from L3 to L1, or you move it directly from memory to L1, right? So if it is in any higher levels, you move it from that level. Of course, memory you will keep it, because the inclusion exclusion is only within the caches, right? But if it is in L2 or L3, you remove it from L2 or L3 and then move it to L1. Okay, and when it gets replaced from L1, optionally you can actually copy it into L2 or L3 depending on wherever you have space. Such kinds of caches are called exclusive caches. They create certain complexity in implementing cache coherence protocol, because you have to look into all the levels to see whether the block is there or not. Okay, but otherwise they are good in terms of utilizing the cache capacity well. Okay, the last kind of cache is also called non-inclusive, non-exclusive caches, which do not make any guarantee about inclusion and exclusion, right? The blocks are brought in through all the levels, and when they are discarded from any particular level, there is no specific exclusion which is done in the other levels, right? So these are some levels of details I'm going to skip. The Intel processors typically follow this so-called non-inclusive, non-exclusive caches. Okay, now let's spend the next 20 minutes or so on virtual memory. Again, I'll try to quickly talk about virtual memory, because you would have seen this in your operating systems course in the undergraduate level. But later on, we will talk about how this virtual memory can be related to the virtually indexed caches. So this is the quick idea about virtual memory. We can talk about two different processes, and these two processes may be talking about the individual addresses. Like, for example, they may be even talking about the same address like 1000, 2000, and so on and so forth. And these are mapped into the physical memory locations in different places. And therefore, even though they may be talking about the same addresses, right, they may be referring to different memory locations like what you see here, right? And because of this virtual memory abstraction, right, enables several things in the operating systems, right? For example, they make sure that the resource is managed well, That means that it reduces the waste in memory space. You would have seen things about memory fragmentation, internal fragmentation, external fragmentation, etc. But by implementing virtual memory and by implementing using either segmentation or page memory management systems, you will avoid certain kinds of fragmentation. And also the different programs can easily be located in the memory and can be executed, while the programmer thinks that his address space is contiguous in memory. In physical memory, they need not have to be contiguous. They could be in disjoint sets of locations, right? Virtual memory also ensures protection mechanisms. That means that one user process address space is not seen by other user processes. It also ensures isolation. That means that any problem or fault in one, corruption in one, does not necessarily corrupt the other processes and so on. Okay. So we talk about this notion of a virtual memory system, which could either be implemented using page-based memory management systems or segment-based memory management systems or base and bound kind of memory management systems and so on. We will only talk about the page-based memory management system in the next slide. So in a page-based memory management system, the virtual address is divided into a number of pages, each page consisting of something like either 4 kilobytes or 8 kilobytes or 16 kilobytes of contiguous locations. And the page size is either 4 kilobytes or 8 kilobytes. Right? Typically, we talk about a 4 kilobyte page size. And page is the basic unit of transfer between the secondary storage and the main memory. Right? So, that's the thing. Sorry. Okay. And what you normally do is that the main memory is also divided in the size of pages, and the pages from the main memory, and pages from the secondary memory are brought into the main memory, right, in chunks of okay, yeah, okay, and this is the unit of transfer from the secondary storage to the main memory, and allocation is also done for these different pages. Okay, and you have to now transfer these virtual addresses into the physical addresses. Let's see how you do this in the case of a page-based memory management system. Okay, let me very quickly talk about the terminology here. A page fault refers to the case that when the required virtual page is not there in the memory, and in this case you have to bring the data from the secondary storage to the main memory, and this typically causes a large amount of delay. Address translation refers to translating the virtual address to a physical address. Virtual address is the address used by the processor, and the physical address is the actual location which is accessed in the memory location. Right? The page fault penalty could be very high. It could be in the order of milliseconds. Right? And typically the page fault ratio is very small. And the page fault is typically handled by the operating system. Okay, now let's talk about the page-based memory management system and how exactly is the mapping done in the case of a page memory management system. The entire virtual address space is allocated in the disk, but then not all of it would be available in the main memory, right? So the way in which it is done is very similar to the way in which things are mapped in the caches, except that the placement policies is slightly different. There is something called a page table, which essentially keeps track of the mapping of each of the virtual pages and where exactly they are residing in the physical pages, right? So the page table is essentially a mapping which says that each virtual page, where exactly they are allocated in the physical address, right? And each process has its own separate page table. And we will see how the size of the page table varies after we look at what is the page table. So for example, let us say if a process generates a 32-bit virtual address, and let's say that each page is 16 kilobytes, then what you do is that you take 14 bits as the offset within a page, and the remaining 18 bits corresponds to the virtual page number. So for each one of the page, there is an entry in the page table. That entry tells you where that page, if it has been allocated in the main memory, is available. What is the physical page number of that page? So by taking this virtual page number as an index and indexing into the page table of that process, you could actually find out where the page exists in the physical memory. So this physical page number is taken and you concatenate it with the offset, and that gives you the address in the physical space where this location could be found. Okay, there are of course these privileged bits and then the valid and dirty bits which are there as metadata. We will not go into the details because they are not very interesting from our points of discussion. They are interesting from the operating system perspective. Okay, so this is how the address translation is done, right? And now you can see that if I am having a virtual page number of 18 bits, then there are essentially 256 kilo locations, 256k locations in the page table, right? And if each one of these entry consists of, let's say, 8 bytes of information, then essentially I have 256k into 8 bytes, which is close to about 2 gigabytes of information. That's exactly how big is my page table, right? The whole idea of page-based memory management system is that you want to allocate space to each process at the granularity of a page, right? And therefore, if you want to allocate things which are beyond a page size, right, that's against the philosophy of this page-based memory management system. And also, if you want to allocate, let's say for the page table, something like 2 gigabytes of storage, right? Not all processes will use all the address spaces. So much of this 2 gigabytes of space that you have allocated may be wasted. Okay, so the page table itself, this simple view of having a linear structure may not necessarily be the way in which it is actually implemented. We will see the detail in one of the later slides. But before that, let's also look at one complication which was introduced by this virtual address mechanism, translation mechanism. Now, if you want to access a memory location, the processor emits a virtual address. Now, that virtual address has to be translated into a physical address. And to translate this physical address, you have to access the page table. The page table itself is stored in the memory. That means that to index into this page table and access this entry, you have to perform one memory access. And after that memory access, you will get the physical frame number, and then you will get the physical address, right, of the data which you want to access. Then using this address, you have to access that location and get the data. So essentially, you are talking about doing two memory accesses for doing one memory access. Two accesses are incurred for each memory access, right? That essentially doubles the cost of memory accesses, right? And again, this is going to be very expensive. So one way to reduce this expense of, I'll skip this details about page replacement and other things which follow, something like, again, either an LRU policy or a second chance policy and so on, right? Let's go to the translation look-aside buffer. So again, coming back to this problem of incurring multiple memory accesses, to reduce this multiple memory accesses, what we do, right, is that we implement something called a translation look-aside buffer, or a TLB, which is very similar to the caches, but it is exclusively used for holding the entries from the page table, right? The TLB is again organized in a structure which is similar to the cache organization, but a TLB is typically small. It's something between 16 entries or 128 entries or 512 entries. It's again set associative. It basically stores the translation information. Some of the pages which have been recently accessed, or the translations which have been recently accessed, are essentially what are cached in the translation look-aside buffer. So let's see what happens if I have, let's say, a 128 entry 4-way set associative TLB in this case. So what I do is that if I have a 128 entry TLB, and if it is a 4-way set associative, then there are 128 divided by 4, that is 32 sets that are available in the TLB. So to index these 32 sets, I need 5 bits of information. So I take the least significant 5 bits from my virtual page number and I index into that particular entry or particular set in my TLB, right? So I take those 5 bits, I index into that particular set, right? And this set may have up to 4 entries because this is 4-way set associative. If one of those entries match with this particular virtual page number by matching the tag with the tag bits of the virtual address, then that particular TLB consists of the address translation. Then I take the physical page number and then I concatenate it with the offset value to get the address translation. If none of these entries have a matching tag, that means that this is a miss in my TLB. That means that none of these 128 entries contain this address translation. Essentially, we're looking only at the 4 entries because it's a 4-way set associative TLB. If they do not contain the data that you are looking for, then it's a miss in your TLB. And in this case, you have to actually access your page table. And only in those cases, you incur 2 accesses. Whenever it's a hit in the TLB, you incur only 1 access. Whenever you have a miss in the TLB, you have 2 accesses. Okay, now let's just see one last complication here, which is basically what happens, right, if my page table size is very large. Particularly if my address space size, for example, in today's context, we talk about a 48-bit virtual address space. And for a 48-bit virtual address space, the number of entries in the page table itself could be 2 to the power 36. And the size of the page table itself could be as large as 512 gigabytes. It's not possible to allocate this entire thing as a one chunk. And even if you can allocate it, it is wasteful because, right, not the entire virtual address space is going to be uniformly used. It's actually very sparsely used. So for this purpose, right, operating system today actually implement something called multi-level radix tree, right? And this multi-level radix tree is a structure which is something like this. At each level, it essentially has, each node has 500 up to 512 children, right? And at each level, right, there are 4 levels. At each level, each node can have up to 512 children. I'll tell you why this 512 comes into picture. This is for a specific setting, of course, right? And you can see that at any level, if certain space is not being used, right, for example, here, this space is not being used, right, then the entries or the children corresponding to that are not allocated. Thereby, you are essentially saving space. You are not entirely allocating all the 512 gigabytes of space. For example, let us say that there are no children here. Then the space corresponding to them and the tree below that, they are not allocated any space. Right? This is only for the page table. This is not for the data. This is only for the page table that we are talking about. Right? So how exactly is this structure accessed? So let's look at the entire virtual address space. Now in this particular example, let's assume that each page is of size 4 kilobytes. Right? If each space is of size 4 kilobytes, and if each entry in the page table is of size 8 bytes, then in a single page of 4 kilobytes, you can have up to 512 entries, each of size 8 bytes. That is why at each level you have, or for each node you have 512 children, right? Because that corresponds to the number of entries that you can hold within a page, right? Now you take your 48-bit address, leave the least significant 12 bits as the page offset, right? There are remaining 36 bits. And if you have 512 children for any node, then those 512 children is essentially 9 bits, right? So you can divide this address space in sets of 9 bits. For example, you take the most significant 9 bits and index into the root node, which tells you which one of these 512 children you are talking about, right? then you go to that particular level, right? And then use the next set of 9 bits and then you index into that. This is exactly one page. And then if you use the 9 bits, right, you are talking about one particular location in that 4K page, right? And that corresponds to, let's say, this location. Then you take the next set of 9 bits, index into that, and that corresponds to one location. Then you take the last set of 9 bits and then you index it. Then this particular entry essentially holds the page frame number for this particular virtual address. Then with that page frame number, you concatenate the offset to get the physical address of the memory location that you want to access. So this way of going down this tree, right, is essentially what is called as a page walk. So in today's context, right, modern processors and operating systems implement what is called a 4-level radix page table to support 48 bits of addresses. And now if you look at it, if you have to do an address translation, you have to do 4 levels of walk, which means that you have to do 4 memory accesses to do the address translation, right? Therefore, to access one data, you have to do an address translation which costs 4 memory access plus a data access which costs 1 more access. That means 5 accesses, right? Okay. So again, as you can see, this is how exactly the page walk is implemented. And in modern day hardware, right, essentially implements page walk as a hardware walk. This is how it is done in the Intel and AMD processors, right? And the root level page table is pointed by a register called CR3, and then to the CR3 is the base of the radix tree, and from there you try to map this to each one of those levels by taking 9 bits at a time, going down to this. You could also do the page walk in software, but it could be more expensive. The TLB itself is not a single level of hierarchy. It's also like a multi-level TLB hierarchy. The first level TLB hierarchy has something like 32 or 64 entries of L1 TLB. The second level hierarchy consists of as many as 1,500 entries to maybe even about 2,500 entries in the L2 TLB. The first level, right, with 32 or 64 entries is fully associative, or maybe 4 or 8-way associative, whereas the second level is 8-way or 16-way associative. Okay. And typically there is one page walker per processor or per core, but some of the recent Intel processors also implement 2 page walkers so that the page walk could be done in parallel by these 2 walkers. Okay, now those are the details of virtual memory. Let me just take 5 minutes to talk about one important aspect, which is about virtually indexed cache, and then I will take questions for 5-10 minutes and then possibly close the class. Okay, so far when we talked about the caches, we said that there is an address and you divide this address in terms of tag, set index bits and offsets. But we never really answered the question, is this address a virtual address or a physical address, right? If it is a physical address, then you will get that physical address only after doing the address translation. And the address translation mechanism itself is a complex mechanism, as we saw now, right? If it is a TLB hit, of course, it will be faster. But if it is a TLB miss, then you have to do the page walk, which is very expensive, right? And if you're going to wait for all of these things to happen to actually access the L1 cache, and let's say if it is a hit in the L1 cache, right, which is actually one cycle, much of these other things are really much larger than that, right? Even if it is a TLB hit, right, a TLB hit itself takes 1 or 2 cycles. And therefore, if you want to actually talk about a cache hit time, if you want to do an address translation and then want to talk about an access, then you first have to incur a TLB hit, then you have to incur a cache hit. So that itself stretches your cache hit time. Therefore, if you have your caches as a if you have your caches which use the physical address, then the first thing that you need to do is to do the address translation, which by itself takes some amount of time, some number of cycles, even if it is a TLB hit, even if it is a hit in the L1 or L2 TLB, even then it takes some number of cycles, right? That essentially stretches your address translation time. So people have talked about other alternatives here. Let me quickly go to these alternatives and explain what these are. Okay, so people have talked about uh, using some part of the virtual address to start indexing the uh, caches. Okay, so if you wait for the address translation to happen, and after the address translation, if you use the physical address to index into the cache, then this is what is called as the physically indexed, physically tagged cache, or what is called a physical cache. Typically, the L2 and L3 levels are implemented as a physically indexed, physically tagged cache, because by the time you search in your L1 and then see whether it's a hit or a miss, right, address translation, at least using TLB, could have been completed. Therefore, typically your L2 or L3 would be a physically indexed, physically tagged cache, whereas your L1 could be using some part of the virtual address, right, for doing the indexing. So let me explain that with the help of an example here. Let's assume that my page size is 16 kilobytes and I have a 64 kilobyte direct mapped cache with a block size of 32 bytes. Right, with a block size of 32 bytes, a 64 KB cache will contain 2048 cache blocks. Since it is a direct mapped cache, I have essentially 2048 sets or 2048 blocks. To index this 2048 blocks, I need 11 bits, right? And because it's a 32 byte cache block size, there are 5 offset bits. So if I start taking these 5 offset bits from the least significant position, and then I need 11 bits to index into my cache, correct? Now, I take the original virtual address, divide this in terms of the virtual page number and the offset bits. Okay, now if I look at it, only the virtual page number is the one which I am going to use to do the address translation. The offset field actually remains as it is, correct? So if you look at it, when I translate this address, I am going to get, let's say, a 32-bit physical address, of which the offset bits are going to remain same as what was there in the virtual address, but the other bits, the virtual page number is going to be translated into a physical frame number. Now, if I have to use this and then index into the cache, then of course what I do is, this is what I do, I divide this in terms of 5 offset bits and 11 cache index bits and then the remaining tag bits. And then of course in a physically indexed, physically tagged cache, I use this 11 bits to index into the cache, which is a part of my physical address space, right? And these 16 bits as my tag bits, and then do the tag check. Okay. And if there is a match, then of course I use the offset bits to get the particular data value. This is what we assume, this is what we kind of thought about it as when you were talking about using the physical address for indexing the cache and for tagging the cache. This is what is also called the physically indexed, physically tagged cache. Typically, this is implemented in the L2 or L3 level. Now, let's look at what happens in L1 level, right? So let me have explained all of these things. Let's just go into what is called a virtually indexed, physically tagged cache, right? In the case of a virtually indexed, physically tagged cache, I use the cache index bits from the virtual address space, and then I index into the cache. Okay. Remember, in the earlier case, we were using the physical bits, the bits from the physical address space, whereas now you are using the bits from the virtual address space to index into the cache. But as far as checking the tag is concerned, I'm actually using the physical address space. So that is why it is called virtually indexed and physically tagged. That is, for doing the tag check, I need the physical address, whereas for indexing into the cache, I only need the virtual address. Why do we do this? We do this because the first thing that you have to do is to do the indexing and then fetch the data. And after you have fetched the data, only you can do the tag match. So assuming that it takes certain number of cycles to index the data and fetch it, in the same time, if it's a TLB hit, you could also do an address translation. That is why it makes sense to do the indexing using the virtual address and do the tag matching using the physical address. So let me just go back and then talk about one other small point here. So I said that my cache is 64 kilobytes and my page size is 16 bytes, but I also assumed that it is a direct mapped cache. If I have used, let's say, a 4-way set associative cache, right, then out of these 2048 blocks, I would form 512 sets. And to index the 512 sets, I would require 9 bits of index. And if I talk about 9 bits of index, right, after 5 bits of offset, the total number of bits will be, for offset plus index, would be only 14 bits. And the least significant 14 bits, whether I talk about it either in the virtual address space or in the physical address space, they would be the same. So if my cache size happens to be such that my cache size divided by the associativity is same as the page size, then the indexing can be entirely done just using the virtual address space. Right here, look at it. Let me just go back here and then show you. Right here, the indexing is actually using some bits from the page offset and then some bits from the virtual page number. But if it so happened in this example, if it is a 4-way associative cache instead of a direct mapped cache, then I only require 9 bits. And those 9 bits would have been entirely within the page offset bits. In which case, whether I call this as virtual address or physical address wouldn't really matter, because these 14 bits are not changing between the virtual address and the physical address. So in those cases, a virtually indexed physically tagged cache would behave identical to a physically indexed physically tagged cache. Okay. The other variations that you can have is what is called a completely virtual cache, in which you actually use only the virtual index and the virtual tags for doing the matching. And as long as there is a as long as there is a cache hit, right, you already got the data from that you are looking for. You don't even need to do the address translation. Address translation needs to be done only when you have a cache miss. There are certain issues with virtually indexed caches or virtually tagged virtually indexed caches or virtual caches. Okay, so one important issue that you will come across is that when two different processes talk about the same virtual address, then they map to the same location in the cache. How do you distinguish between them? Right, to distinguish between them, if you are doing multi-programmed kind of a thing, then whenever you do a context switch, you have to either flush the cache, or along with the tag, you also have to store information about which process to which it belongs to. This is also called the address space ID. Typically, modern processors have this notion of storing the address space IDs, which identify which process it is. Okay, that is one particular problem. The other problem is that in programs, you also have this notion of aliasing, two different virtual addresses pointing to the same physical location, right? You also have the other way around, right? Two different processes which are using the same virtual address, now mapping to different physical locations. How do you distinguish between them, right? That you use it using ASIDs, address space IDs, whereas if there is an aliasing, then there is this problem is called the synonyms problem, right? That has to be solved in a different way. Okay, so these are some specific issues with regard to the virtually indexed, virtually tagged, or virtually indexed, physically tagged caches, right? So with that, we will kind of conclude our discussions on caches. That should perhaps give you enough idea about what is needed to be, enough idea about caches for you to understand the rest of the discussions. So let me stop here. I have run 15 minutes late, but if you have some quick questions, I can possibly take them now.
So,
Yeah.
hello. Am I audible?
Yeah, you are. Go ahead.
So, I didn't quite understand like what was the advantage of having Redux tree. Like, if suppose we have the Redux tree in the memory itself, then it requires 4 access for each individual memory access to access the data. And if it is in the page table itself, then also like it doesn't have any like it show any
No,
advantage.
the problem is the following thing, right? Radix tree is not an option. I mean, it's not an alternative. It's the only option that you have. When you want to support something like 48 bits of virtual address space, it's not possible to have a single level page table structure. Okay, so you are comparing it with the previous single level page table structure, isn't it?
Yes, sir.
Right? This particular option is not there because if you have a 48-bit address space, this table itself, as I was explaining in one of the following slides, itself is something like 512 gigabytes of space. Right? First of all, in your processor, you may not have 512 gigabytes of memory, right? And second, even if you have that much of memory, right, to allocate contiguously to one process 512 gigabytes of memory just for the page table, not for the data, just for the page table is impossible. So your system, how much memory does it have? 8 GB, 16 GB, correct?
Yes, sir.
And that is the memory that you have for all the processes and for its page tables and for its data and for many other things. You are talking about just for one process and just for the page table requiring this much of memory if you want to allocate all of them together, right? Allocating them contiguously is a problem. Allocating this much space is a problem. Not only that, this is a problem. Even if you have huge memory which you can allocate, which you can waste, it's all a waste because this entire address space is going to be used. Only a part of this address space is going to be used. Therefore, allocating things linearly is wasteful, right?
Yes, sir.
So think of this as an analogy to think about is that let's say if you're building a binary search tree, right? Building this binary search tree using a tree data structure is far more efficient, right? Let's talk about this binary search tree for the words in the English dictionary, correct? It's far more efficient to implement this as a binary search tree. It's actually very, very inefficient if you want to allocate arrays for all of this and implement it, isn't it? So that's exactly what you are comparing with, right?
Okay. All right. Thank you, sir.
So it's not that should I do this or whether that is an advantage or this is an advantage. This is not feasible at all. You can't allocate a single page table of that large a size. It's not possible, right? If you have to have holes in this, the way that this works is that this is contiguous and you have all the entries available. That's why you are able to index and then get the data value. It is okay if you have, I mean, even if you have 18 bits, it's not going to be feasible, okay, because that itself is very large. But if you have 48 bits, of which, there are 36 bits of physical page number, to allocate this large a size and then to allocate it contiguously is not feasible. Therefore, your only option is to implement this as this. And that is why you do this. Your Linux operating system implements this radix tree, right? It supports actually multiple page table sizes like 4 kilobyte page sizes and 2 megabyte page sizes and so on. But the base information 4 kilobyte page sizes is implemented using this radix tree page table, right? So your initial view that the operating system where you have a single level page table, right, is primitive or is just the initial part of it. You are not really seeing how exactly it looks in practice, right? That's one of the reasons why I wanted to quickly introduce that, even though I was kind of hurrying through it.
Okay. So, like, could you briefly again explain the structure? Like, what exactly are the 512 entries in each node of this
Okay.
tree?
So it's a little bit complicated, but you can think of it like this. So there is this root level structure, and this root level structure is pointed by one hardware register called CR3. So the CR3 essentially holds the address of where this root level entry would be available. Okay. So the starting address is basically what is stored in the CR3. Okay. Now the starting address, from the starting address, 4 kilobytes of information, page table information, is stored in this root node. Right? Each node is 4 kilobytes. Okay, and in this 4 kilobytes, you can actually hold 512 entries of page table information. Right? Each of these 512 entries corresponds to a pointer to the next level, because remember, each node has 512 children. Right? So those 512 children, where exactly they are located in your physical memory, that physical address, right, is stored as a pointer in these 512 entries. Okay. So which one of the 512 entries you need to access is essentially given by these 9 bits which are over here. For the root level table, it is the most significant 9 bits. For the next level, it is the next 9 bits. For the next level, it's the next 9 bits, and so on. Does that answer your question?
Yes, sir. So,
Okay, so at each level, at each node is a 4 kilobyte entry, right? That consists of 512 nodes, or information about 512 nodes, and each one of them is a pointer to where that particular page is. Okay.
okay, sir. So,
Yeah.
so we in some slide we also talked about like parallel page walking thing. So, like, how exactly does that?
Sorry. What other working? I didn't get you.
So, like, we talk like this, like some Intel processors have like two page walkers for a single
Oh,
read.
2-page walk. So okay. So just one page walker, right? What it does is that, given an address, given the CR3 register, right, it has to walk through this multi-level tree to find out what is the physical address of that particular page. Correct. You have to walk through these 4 levels to find out what is the physical frame number of the address that you are looking for. This is the virtual address. Okay, this is the 48-bit virtual address. Now you took this corresponding bits, walked through this tree, and then finally got this physical frame number. Correct. This is done by a hardware walker. This is not executed as a sequence of instructions, because that would be too expensive. Okay. So there is a hardware walker which essentially tries to do this. It of course reads the memory, but then it does the other steps in hardware. Right.
Okay. So,
Okay. So if you have to implement this purely in software, you can say that, okay, read this and then go to the ith child, right? Read the pointer, then pointer is equal to pointer dot something, right? You can write a program like that and then you can implement it. That would be more expensive to walk through the tree, right? So that is actually implemented using a hardware. That's what I meant as the page walker hardware, right?
okay, sir.
Okay.
So,
Now there are 2 such hardwares in Intel processor, in most recent Intel processor. That's an additional level of detail you can actually skip, right? Your question that you have to ask is that, who does the page walk? Right? You can say operating system does the page walk, but if operating system is going to do the page walk as a program, right, as a sequence of instructions, it's going to be very expensive. That's what I was trying to explain in one of those slides. Maybe it was subsequent to this. Yeah, this slide was trying to say, right? You can either do this page walk using a hardware or using the software. Okay, a OS handler will actually do the page walk by executing it as some kind of a program, but that could be slower. Yeah, I believe you have one more question.
Yeah, so basically, so my doubt is like I got this point, like how parallel page walking thing can be handled, but basically
Not parallel in the sense of the tree can be walked for a single request in parallel, right? But there could be multiple requests,
oh, okay, I got. Oh,
right? There
I
could be
thought it
two
was
load instructions, or there could be load instruction from process 1 and there is a load instruction from process 2, right? Those two loads can be done in parallel, or those two address walks could, or sorry, those two page walks could be done in parallel.
okay. Yeah, so
Obviously, the walk within I mean for a single request is sequential because you have to go through the tree, right?
yes,
Means you can't just do this in parallel. Okay.
yes, sir.
All right. Again, if you see that you are seeing too many new things, that's a good thing, because this the idea of this workshop is to actually get you introduced to some of these newer topics, as well as what's really happening in actual implementations and hardware, right? So far you have been given a simplified view of things, but then it's time to come out of that and then understand what's really happening, right? So certain new things that you are hearing, but only hearing some very brief information or partial information about them, are actually good pointers for you to go and read more about them, right? Obviously in this 1.5 hours we can't teach you everything, but if we can give you enough pointers or excite your curiosity to go find out more about them, then the purpose of this 1.5 hour lecture is really served. That's really what we are hoping to do for. All right.
Sure, sir. Thank you.
Sure. Any other questions?
Sir, I have a question. So now
Sure. There are two,
page access
one
is,
by one. Yeah, go ahead.
sorry. Rahul, you can go ahead, please.
No, it's fine. You go ahead.
No, it's please go ahead. Please go ahead.
Right. Okay. Yeah. So you mentioned that radix tree is not an alternative, but it's like a necessity that is needed.
Correct.
So
Correct.
what would be an alternative?
Okay. So people have talked about whether page-based implementation is the only way to do implementations. People have talked about bringing back segment-based implementations as another alternative. People have talked about how to reduce the depth of the radix page tables, radix tree, right? Typically, this radix tree for 48 bits is 4 level deep, right? And if the virtual address has to be extended to 57 bits, there are discussions already on that, and certain newer processors are going to implement a 57-bit virtual address. Then there the radix table is 5 levels, right? So people have talked about alternatives which are either segment-based implementations or alternatives which look at a completely different way of organizing the radix page table, and so on and so forth. Okay. People have also talked about how to short circuit the walks in the radix page table. Okay. There are some interesting discussions. So one simple thing that I can tell you is that, let's say when you do this walk, correct? Which of the memory locations have you actually accessed from the memory? You have accessed this memory location. You have accessed this memory location. You have accessed this 4 kilobyte locations. Correct? And then finally you got this information. But let us say when you got this 4 kilobyte locations, right? When you access this particular location, right? This is 8 bytes. But when you brought this 8 byte to access, you would have brought it into the cache. Correct?
Oh, right.
And along with that, you would have brought the adjacent 32 bytes, which means what? Maybe when you brought this, you brought a set of 4 entries into the cache. Correct? Which may be there in your L1, L2, or L3 cache. So the next time when you want to access this entry or some other nearby entry, right, you may not necessarily go to the memory. You may possibly get it served from your L1, L2 or L3 caches. Correct? But now look at this particular entry, right? This is at a higher level in the radix tree, right? This entry is more likely to be found in your L1, L2, L3 cache as opposed to this entry. And for that matter, this entry is even more likely to be found in your L1, L2, L3 cache as opposed to this one. So there are also alternative cache structures which are meant specifically for holding the page table entries, which are what are called as page walk caches. So those were some of the other things that people have talked about. One other thing people have talked about is to reduce the page table size itself by increasing the page size, maybe talking about 2 megabyte pages or 1 gigabyte pages and so on, or using a combination of them. Those are the other things that people have talked about. Lots of interesting research have happened in the, in the recent times on these activities. I would be happy to talk to you more about this offline if you send me a mail. I can point to you. And one of my colleagues is actually working on some of those interesting aspects.
Sure.
Yeah.
Just one thing that I found interesting about what you said. So if you have a separate page walk cache, how
Right.
would that affect the working of a TLB? Would it come after or before?
It would come after the TLB. The TLB is your first level reach, right? If it is there in the TLB, very good. You are done with the address translation. Because see, essentially, if you look at it, what does the TLB caches? The TLB caches this information.
Correct.
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 So it actually gives you the final answer. Right?
Right, but
which gives you the final answer in terms of your address translation.
Correct, but both of them almost hold the same information.
No, the other fellow holds you this information. Then after that, you have to do this walk and get it.
Correct.
Or it holds you this information, right? And after that, you have to do the remaining walk.
Right.
So in some sense, this holds you the final answer. TLB gives you the final answer, whereas these page walk caches gives you these in-between stage answers, right?
Right.
So that's where the difference is.
Right. So maybe in association with that cache and the TLB working together, you can maybe formulate policies like how you would do
Absolutely.
for
Absolutely.
cache.
Yeah.
Right. Okay.
So what to cache, where to cache, what should be the replacement policies for them, right? They're all very different. So for example, if you look at some of these levels when they are cached into your L1, L2, L3 caches, right? There is no way to distinguish them from your regular data versus page table data, right? And they are all mixed up in that, and that causes certain amount of difficulties as well. Okay, again, people have looked at some of these aspects as well. I can point you to relevant literature on that.
Right, I will definitely send you.
Sure. Contact me in my email address. I would be happy to connect you.
Sure. Thanks.
Okay. I think there was one more question. I would be happy to take that as well.
Yes, sir. I had a question, but I think I got the answer. So essentially, I was asking that this translation now becomes very expensive. So you already talked about these.
The translation has become very expensive, and if you want to hear something more, right? When you want to do this address translation in virtualized environments like clouds, right? That's even more expensive. Okay. So just to give you a very rough idea, address translation in a radix tree walk takes 4 memory accesses for doing a single address translation. But if you have to do this in a virtualized environment, the worst case number of memory accesses is 24.
Oops. Okay.
Of course, not all of this is incurred, but that's the number of steps that you have to go through to do the address translation in what is called a nested page walk. Okay, nested walk. Okay, again, people have talked about how to improve that. Right? From that 24 all the way down to 2 or 3 or 1 is essentially what people are talking about. In the best case, you want to reduce it to 1 in 99% of the time. How do you do that? Right? There are lots of interesting things. So to understand or to appreciate all of them, the first thing that you need to appreciate is that in practice, this is what is happening, right? I mean, it's no longer people talk about a single level page table. It's not just no longer, right? I don't think it was there ever in the last 20, 30 years. But we have only been teaching that as a part of our operating systems course, right? So that's the reason.
Right. So these page walk caches, they sort of cache like they cache things at every level, or
they cache the page table information typically at the second and third level.
okay.
The first and again, there are some reasons why they do what they do, right? I mean, it's again to do with the locality and which is more cacheable or which is more beneficial and so on and so forth.
Right.
Yeah. Again, I'm not. Again, I don't remember all the details on the top of my head. This is not my area of interest or research, but I have one student who has recently looked at it, and that's why I got excited about it.